Hi class, how are things? So here we are, week 3. So hopefully you're not gone too daft sitting at home and the house is cooped up. Alright. What we're going to do is, so last week we had trigonometry, we'd finished that, moving on. So kind of keeping the same sort of theme in trigonometry based on triangles. We want to look today at chapter 16 in similar triangles. Okay, we're going to be looking at these. There is similar shapes, similar triangles, a little bit on circles and that in it. Then after that we'll move on and we'll look at congruent triangles and a few theorems. So that'll have a lot of that section then tidied up for us. So for anyone not in our class that might be possibly tuning in, so it is our Text and Text 2 higher level book there that we'll be working off of, and it is chapter 16. So what we're doing here first of all is our similar shapes. Okay, so if we just look at on the left hand side first of all, so we have two shapes, okay, 1 and 2 with them called here, and they're similar enough, right? They're both, if you were to look at them there, they've got all right angled corners in it, alright? So they've got two of them then have this little section missing in the middle, alright? This is higher than this is higher than this. So we can pretty much say that they're the same shape, but of a different size, alright? They're fairly similar. So if we look at the sizes then of the sides, so we're told over here that this here is 6, right? We're not so 6 centimeters, 6 meters, whatever. So this is 6 and this is 4, and this bottom side here is 8. If we look on the larger of the two shapes, we can see that this is 12, B, and 8. And if we compare the two, so we'll take this longer side here and this longer side here. This is 6 and this is 12. Is there any similarity there, a ratio there that we could look at between the 6 and the 12, but also the 4 and the 8, right? 6 and 12, 4 and 8. So we can see that the measurements in the larger triangle, or the larger shape here, is actually twice of the smaller one, okay? So we can see, deduce that from these two given measurements here that we're given, that this shape number 2, is twice the size of shape 1, alright? So we can say there that if we look at the length A and the length B, alright, so we'll create a ratio there, A to B. B is going to be twice whatever the size of figure A, alright. So we have a ratio, we've created a ratio based on 1 is to 2, alright. So this is double this, so whatever A is, B is twice it. So whatever A is, B is going to be twice it. And that's kind of the idea, the premise that we'll be working on in terms of our similar shapes. So if we take that's just a similar shape, we'll move it over now onto our triangles. Okay, a lot of this is based on similar triangles. First of all, we have to identify, we're given two triangles, we want to figure out, are the two of them actually similar? Alright, and what makes a similar triangle or a similar shape? We want to have it that it has the same angles, alright, and it has the same number of sides and all of that. So first of all, we can see that, well, these are two similar triangles. Why? Because this angle here and that angle here are equal. This angle and that angle is equal. And the third set of angles is also equal. So if the three angles are all equal to each other, then we can say, yes, these are two similar triangles, except sizes is different. So this one is smaller than this one. Alright, so now we've identified that yes, these are two similar triangles. We can use the idea here of sizes and ratios to work out unknown lengths. So you can see here we have an X and a Y marked in. We want to work out the length of both X and Y. Okay, so there's two ways that we can go about it. The way I'm going to show you first of all isn't the way that we're going to necessarily maybe work through the whole lot of them, alright? But it's based on the idea of our ratios. So if we look at two sides that we know, alright, we know 6 and we know 9, alright? And we were going from this angle to that angle, this angle to that angle. So these are both what we call corresponding sides, alright? So the length of the smaller one, alright, is in a given ratio for the larger one. So 6 units 9 units. And if we simplify that down, well, 3 will go into both of these. So we can simplify this down. So this is 2 is to 3. Okay? So we can see that the ratio of the size of the small one to the size of the larger one is in a ratio of 2 parts is to 3 parts. Okay? And we can use that ratio then, alright, to work out both x and y up here. So, if I take the length of side 4 here, what side corresponds with 4 in the larger triangle? Well, is x. Alright, so if we look at 4 is to x. Alright, well that has to also follow this given ratio of 2 is to 3. So if this is 2 parts, alright, so we'll put it up here maybe in red. So it has to be 2 parts is to 3 parts, right? So if 4 is equal to my 2 parts, what would be equal to 3 parts? Well, 2 goes into 4 twice, so 1 part is 2 units long. 3 parts is 3 by 2 will be 6 units long. So we're going to end up getting 4 is to 6. So basically I have now worked out that x is equal to 6 units in length. Alright? So you're using a ratio. So 6 is to 4, or 4 is to 6, reading from left to right. Alright? Do the same idea over here with x, or with y should I say. Alright? So 5, what side corresponds with the side of 5? Well, it is y. Alright? If 5 is equal to 2 parts, what is one of those parts? 5 divided by 2 is 2.5. What then is 3 parts? Well, it is 2.5 multiplied by 3, which will give us 7.5. Alright, so I have quite simply and quickly worked out, using ratios, the length of x and the length of y in my larger triangle. Okay, so 7.5 for y and 6 then for your x. Nice, quick, easy to do with the ratios. Alright, the way now that we're going to look at in a second is to set up equations. Alright, and we'll just do it here again for us rather than let them back over what I've already done. Alright, the reason that I'm kind of doing it this way is because this lends itself better to other parts, other questions and that. So it's nice, this is a nice easy one to start off where you can straight away work out a ratio. The other one is maybe it leads us more into sort of stuff we'll have to do later, kind of transversals and that sort of stuff. So I leave these up here because we know what the values of them are. Okay. Again, we're working with the idea of corresponding sides. So where first originally we were working with ratios, now we're going to create an equation where we have 4 parts, which is generally 4 sides, and we have one unknown out of the 4. So if we look at this length here, 4, and this length side here of 6. We know the 6 corresponds to the 9, so we know that this length is 9. But we don't know this length x. But we know that 4 corresponds with x, 6 corresponds with 9. So I'm going to use the 4 of these sets here of lengths, and I'm going to be able to use that to work out my length of x. Alright, so I'm going to create a fraction. So 2 corresponding sides, one all over the other. Now I could put the x all over the 4 or the 4 all over the x, it makes no difference. I'm just going to go from left to right. So I'm going to create a fraction. 4 all over x. Smaller triangle, same side in the corresponding larger triangle. So 4 from this one, x from this one. That then is equal to 2 corresponding sides that we already know because we've got our unknown here. So 6 corresponds to 9. We went with the small one first with the 4, so we have to go with the small or triangle here. So 6 all over 9. So now we have an equation set up with one unknown. Simply cross multiply. We're going to get 6x is equal to 36. X is equal to 6. So cross multiplying 6 by x, 6x, 4 by 9, 36, and dividing both sides then by 6, we'll get x is equal to 6. Do the same thing over here for y. So 2 corresponding sides in both triangles with 1 unknown. So we'll stick with the 6 and the 9 because we both know those, and we now have to work with the corresponding side with 5 and y. Alright, so we'll go for the smaller triangle first. So 5 all over y is equal to 6 all over 9. Cross multiply. 6y is equal to 45. Divide both sides by 6. Y then is equal to 7.5. Okay, so again, now we will solve 2 ways. The first way was to do with our ratios. Nice, quick, and probably a faster way to do it, if you're able to do it that way. This way, I like it a little better in that it lends itself to what we'll be doing later on with transversal and that sort of stuff. Alright, but how do we do it? You need to get 2 sets of corresponding sides where you have only one unknown. And we simply then cross, multiply, and solve for our unknown in each case. Alright, so just finishing up on that last point that we were doing there, it leads us into our first theorem. Okay, and that theorem basically states that the triangle ABC and triangle DEF, if we can say and prove that those 2 triangles are similar, then we can say that their sides are proportional in length to each other. So here we have one triangle, here we have a second triangle, and we set up 3 sets of fractions in terms of sides that are corresponding to each other. Alright, so these are all corresponding sides. And what we do is to work out, say if we wanted to work out the length of DE, okay, we would forget this third set of corresponding sides here, and we'll simply be dealing with 2 sets in here. Alright, we have 4 lengths, we have 1 unknown, and we can use the other 3 to figure out the 4th. And that's basically using your corresponding sides and the fact that your triangles are similar. Okay, there is your first theorem. You don't really have to learn it off, but you do need to be able to use it in practice. So it's not a theorem that you have to recite, but yes, you do have to be able to know how to work with it in practice. Okay, so the last section there that we're looking at finished up for the exercises of 16.1. So this is moving on now to 16.2 and what we call transversals. So if we look here and we just talk about the theory of it before we start, alright, so we have 3 sets of parallel lines, and we know that they're parallel because we can see these 3 arrows here and they're all pointing in the same direction. So A, B and C are parallel lines. We've got a 4th line here, P, and that is cutting the 3 lines A, B and C. And what we can see is from that here is that measurement there and that measurement there, the length of those 2 sets of lines is equal. So when we have a series of parallel lines and it is cut by another line, so in this case a 4th line P, that will result in equal lengths of line P. Okay, so that length there and that length there are equal. Alright, so that's the idea of a transversal, and if we bring that transversal into the idea of a triangle, okay, so forget about that here down here, we look at this one for the first. Alright, so we have a triangle ABC, and we have our couple of sets there of parallel lines. Alright, so BC, that bottom base, this red line and that red line, those 3 lengths are all parallel. Alright, and what the measurement here in space in between these 3 is equal. Alright, so that has resulted in 3 equal sides. So the line AB has basically been divided into 3 equal parts. Same going on here with A and C, 3 equal parts here. So if we have a series of parallel lines to any given edge in a triangle, it will result in the other 2 sides being divided into the same ratio. Okay, and in this case, they're all equal. Okay, that is it, and that we'll have a look at in a second. That's one of our theorems. So when we've got a side of any given side of a triangle is parallel cuts are made, then it will divide the other 2 sides there up into even parts or into a ratio. Alright, it doesn't have to be even. So we'll have a look at the idea when it's not even. So down at this larger triangle down here. So we have the base, again BC. We've got a series of horizontal cuts that are parallel to the line BC, okay? And we can see, well, how many of them have we? We've got 1, 2, 3, 4, okay? But only one of them is in heavy, all right? So that's the one that we're concerned with. We're not really concerned with the ones that are in dotted lines here. All right, so if we look at the number of parts, how many parts is side S? All right, well, it is 2 parts. And if we look at the gap distance here from T, so we've got 1, 2, 3 parts. Okay, so we can see our line here, A to B, that has now been divided into 5 equal parts, because remember the spacing of these are all equal. So we have 5 equal parts, but the ratio of S is to T is 2 is to 3. Same over here on the line AC. This is 2 parts, this is 3 parts. So the line AC has been now divided into 5 equal parts. Alright, so say I told you that the length of side T was 9 centimeters. Work out X. Okay, well, if I know here, what is my given ratio? T is to S. So T is to S is 9 is to X. Okay, but we know the number of parts, we know the ratio, we know it is 3 is to 2. Alright, so if this T is 3 parts is to 2 parts, what is X? So 3 into 9 goes 3 times, that 3 by the 2 is going to give me 6. So it is going to be 9 is to 6. So we're able to now work out the length of an unknown side based on the ratio given by these transversal cuts that are made. These are horizontal cuts because this is a horizontal line, but they could also be at any other angle. Okay, so I'm not going to, there's another example I was going to do where I'm going to skip that. Look at the example on your books, page, how are we here? Alright, page 318. So if you look at your books, page 318, also look at the notes that I've given you, and that will basically explain that further if you need. Alright, but you shouldn't really need it. I'll just maybe, we'll do question, I'll do question 1 here just for us. I don't even need to rub this out actually. Alright, so we'll put in this here. So this is question 1 there out of the exercise 16.2. I will put in another transversal line here. Okay, and we're told 8 and 8, 8, 8, this is 10, this is X. Alright, we want to basically find out X is equal to what? Okay, well, we're told here that A, B and C are 3 parallel lines. The spacing of them is equal, and we know that it's equal because from here to here and here to here is 8 and 8. So we know that these lines are equally spaced. Okay, we can see over here because this line is at a different angle, so that length is something other than 8. If this line P and that line there were parallel, then it would be 8 and 8. But it's at a different angle, so that length is different, and it's 10 in this case. But we know that from C to B is equal from B to A. So X here has to be equal to 10 also. Alright, and that's basically the premise of these transversal lines here you're building on. The harder questions, you'll use ratios where 8 might be to 16, alright, so they're not of equal spacing, but that's the type of thing that we're looking at there. Okay, so continuing on with chapter 16 there on similar triangles, we're moving on now to angles and circles. Okay, so there's a few things there, there's 3 or 4 of them that are coming up, which are kind of just a couple of facts about our circles and basically kind of leading into theorems. Now, these are kind of what's going on here. You need to be able to know and remember them, alright, and know what's going on, but you also have to be able to prove them. So some of these are in the proofs that you have to do. Okay, so I'll talk about this and then we'll go through the proof in each case. Okay, so the first one here is where we have a circle, all right, and we have a line AB, which is a diameter line. And if you're unsure of any of the parts of our circles, I would tell you to pause now, go to the section, I think is page 323, I think, or something, on your circles, learn the parts of it, and come back to us. So, assuming that you're all fully up to speed on our circles, we have a diameter line AB, okay? If we have a triangle where one of the three sides is a diameter line and the other is standing on the circumference of our circle, then the angle at the circumference is always 90 degrees. So it doesn't matter where point C is, as long as AB is a diameter line, then that angle will always going to be 90. And we'll go through the proof now of it. Okay? So to prove that, first of all, I need to sketch in or draw in a line joining C to O. Remember, O is the center of your circle. So I'm going to just join in this line from C to O. Okay? And I'm going to now label the angles. Alright? So, well, before I do that, A to O, O to C, and O to B, they are all radius lines. Okay? So the three of those lengths are equal. So that length, and that length are all equal. I have now divided my larger triangle into two smaller triangles. And if I look, well, that length and that length in this triangle are equal. So what type of triangle have I got? I've got an isosceles triangle. Alright, so what do I know about an isosceles? I know that this angle here, and we might call it X. I know that that angle and that angle have to be equal. Alright, so this is X and this is X. Alright, if I look at this triangle here, alright, equal length, isosceles triangle, so that angle and that angle are also equal. And we'll call this maybe Y and Y. Alright, now taking and talking a little bit about what do you know about a triangle already. Well, we know the three angles of a triangle add up to give us 180 degrees. So 180 degrees is equal to Y and X and X and a Y. So it's the angle X plus the angle Y plus the angle X plus Y. Alright, tidying this up, we have an X and an X and a Y and a Y, so we'll just tidy it up. So 180 degrees is equal to 2 of the angle X plus 2 of the angle Y. Alright, now if we look, I have two X's and I have two Y's. Alright, so we can say we have twice the angle X plus the angle Y is equal to 180 degrees. So if I take and divide both sides by 2, I'm going to get 90 degrees is equal to the angle X plus the angle Y. 90 degrees is equal to the angle X and Y. Well, if I look up here, X and Y, the two of those added together have to be equal to 90. And there, that's that first one proved for you. Alright, so this next one now that we're looking on to is basically we're talking about the angle at the center of a circle and the angle at the circumference. Okay, so where we have two sets of arcs or two sets of lines here basically standing on the same base points A and B. Now you could join A to B and you could make a smaller triangle AOB and a larger ACB. So you could have two triangles standing on the same base points A and B. Alright, and they're both going either to C and to O for the smaller one. Okay, so what we have here is we can see that the angle here and the angle here. Well, whatever the angle is at the circumference, the angle at the center is always twice whatever that is. So if this was 30, this would be 60. If it was 60, this would be 120, and so on. Alright, so whatever this angle here is, this is always double it. Or whatever this angle here is, this is always half it. So if this was 90, then this would be 45. That basically is one of our theorems, and again, we have to be able to prove that. So how can we take and can we prove that? So as we're finishing up on the last one, right, we were pretty much able to solve the last one because we had formed isosceles triangles. And a lot of these will rely on us creating isosceles triangles to solve the questions. So all I'm going to do is drop in a line from C to O and extend, I'll get rid of O, Jesus, from C to O, and we'll extend it. So there it is, extended. And I'm just going to label in my various angles. So I'm going to label this angle 1, this is 2, 3, 4, 5, and 6. Okay? Now, let's look. Remember, this is O here. Alright, so that's the center of your circle. So, the length from O to A is equal to the length from O to C is equal to the length from O to B. So, we have equal sides. I'll mark them in as being equal. Alright, we have a triangle here, we have a triangle here. So, we have isosceles triangles. So, this angle here and this angle here are equal. So, I can now say that, well, 2, whatever the angle 2 is, that's equal to the angle 1. Similarly, angle 3 is equal to angle 4. So I'm going to rename 2 and 3, going to be 1 and 4. Alright, so 1 and 1, 4 and 4, because they're both equal. Now I don't know how to measure them, but I know that they're equal. Taking then the fact that we know that the exterior angle of a triangle, so if we've got a triangle here, alright, so 1, 2, 3, and 4, if we take the fact that the exterior angle of a triangle is equal to the sum of the two interiors, remember this is another theorem, so the angle 4 is equal to your angle 1 plus the angle 2. Right? I'll finish this is getting a little bit away from this, but we need to know this anyways. Alright, so we know that the angle 180 degrees of a triangle is equal to your three sides, so 1, 2, and 3. So 1 plus 2 plus 3. So the angle 1, 2, and 3 add to give us 180. We also know that 180 degrees is equal to a straight line, so that is angle 3 plus 4. Alright, so if this is equal to 180, this is also equal to 180, then it stands to reason that this has to equal this. So if the two of these are the same thing, the two of them add to 180, then this has to equal this. So we'll let them equal each other. So the angle 1 plus the angle 2 plus the angle 3 is equal to the angle 3 plus the angle 4. We can see here the angle 3 and the angle 3. If we subtract the angle 3 from this side, we have to also subtract the angle 3 from this side. So we're going to basically subtract and cancel in those. So we're now left with that the angle 1 plus the angle 2 is equal to the angle 4. So basically the sum of our two interior angles is equal to the exterior angle in our triangle. So that's what we have here. The angle 4 is equal to the angle 1 and 2. Okay, so we're using that fact back in here. So we'll deal with this triangle here. That's an interior, and that's an interior, and this is our exterior angle. So the angle 4 and 4 is equal to the angle 5. Okay? So our angle 4 plus our angle 4 is equal to the angle 5. The same thing is true for 1 and 1 is equal to 6. Alright. Sorry, 1 second. Alright, so 1 and 1 is equal to 6, 4 and 4 is equal to 5. Alright, what now can we deduce from that? Is there anything that we can deduce from that? Alright, so if we say maybe well, we can double these up, so twice the angle 4 is equal to the angle 5, twice the angle 1 is equal to the angle 6. Alright, so pause the video here for a second. Can you now prove that this angle up here is half this angle here, or this angle is double this, just from what we've done there for 1 second. Okay, so hopefully you have managed to see that if we were to add these two angles together, so angle 5 and 6, so the angle 5 plus the angle 6, well, that is equal to, well, what is the angle 6? It is twice the angle 1. If we look at the angle 5, it is twice the angle 4. So the angle of 5 plus 6 is equal to twice the angle of 1 plus the angle 4. So the angle 5 and 6 here is equal to twice the angle of 1 and 4. So then we have proved it. Whatever this is, it's equal to double whatever this is. Okay, so that's the last of the theorems that we have to prove based on our circles, but circles that are using triangles in the proof to solve them. So if you look at the last page that I'll have attached for you on the notes wise, so if you can just maybe get it for those of you who don't have the notes. All right, so they are basically 4 corollaries there, that basically a corollary is something that we deduce or we can assume is true from having proved something else. All right, so there's 4 of them there. So the first one basically states here, if you can see it hopefully, is that if we have the same base point A and B and we have 2 sets of arcs standing on those both points A and B, then the angle X is equal to the angle Y. All right, so that's number 1. Number 2 over here, we have a cyclic quadrilateral, right, and we can see that the angle 1 and 3, that is equal to 180 degrees, and 2 and 4 is also equal to 100. And if we look at number 3 and number 4 here, these are pretty much the same thing, in that one is saying that if this angle up here is 90, well, using the theorem that we've just proved, then this angle has to be double whatever this is, so this is going to be 180. Going the opposite way, the flip side, that if we know that this angle here in a straight line has to be 180, then half of that is going to be 90 up here. So these are 2 of the 1, basically using the premise of this theorem here, where you're saying that this angle is always twice this. So if this up here is 90, well, this has to be 180, but if this is 180, well, this is half it, which is 90. All right, so that finishes up chapter 16. Drop us a message there in Google Classroom if you need any help. I'll be uploading these notes along with the videos, and best of luck to you. And basically this is covering this week's work. Alright, I will be setting you work over the Easter holidays, but not a lot. Alright, talk to you.